Hello, this video will present the paper, Improved Partial Dependence Plotting for Interpretable Machine Learning. Interpretable machine learning is used to extract information from a machine learning model to help humans understand the model and the decisions it makes. It is considered an important aspect of model evaluation, as any single performance metric provides incomplete understanding of the model's internal process, particularly for important tasks. Understanding black box machine learning models is important, as it allows people to identify biases, increasing model fairness. It also helps with debugging the model, making models more reliable. This increases transparency and fosters trust in model predictions. Partial dependence plots demonstrate how the predicted output of the machine learning model is influenced by the marginal effect of one or two features. However, it is not without some drawbacks, as we will see in a moment. For some machine learning model represented by function f hat, the partial function f hat of s corresponds to the machine learning model's predicted output, given the one or two features in the set S whose effect on the output is to be evaluated. Although PDPs are simple to implement, they have some drawbacks. The most important issue is that PDPs assume no correlation among features. In addition, as PDPs calculate the average marginal effect, positive and negative effects on the prediction from a single feature will cancel each other out when calculating the average for that feature. PDPs are mostly useful for global interpretability. To understand the way PDPs work, we will use a simple dataset that predicts housing prices using the area and the number of bedrooms in the house, as well as whether it's located near a park. If we were to explain a model's behavior using PDPs on this dataset, we would first find the number of unique values for the feature in question, let's say area. Then, we replicate the entire dataset for each unique value in area. In this case, we are replicating the dataset for the value 1000. Then, for 1800. Then, 1500, 1200, and 2000. Then, we get predictions for the new datasets from the already trained model. We compute the average output for each unique value of the area, and we plot the unique values of the area against the average predictions for each value. We will now discuss the challenges associated with PDPs, which include assumption of feature independence, misleading interpretations in correlated features, and smoothing out local variations. The main limitation of PDPs is the assumption of feature independence. For example, if the price of a house is to be predicted, then clearly the area of the house is related to the number of rooms it has. This assumption that the area feature is unrelated to the number of rooms feature is clearly unrealistic, as they are typically correlated. PDPs will generate examples where the largest house area might only have one room or vice versa. To address this issue, we introduce IPDP, which removes all examples that are far from the current example, according to some distance measure. We start by creating a new dataset as we did in PDP. However, instead of taking all the data points, we measure the distance of each data point in the new dataset to the original data point. Then, we eliminate the data points with distance beyond some predefined threshold. We then proceed with obtaining predictions on the trained model as done previously with PDPs. In summary, the IPDP methodology replicates the dataset for feature value variations. Then it filters data points based on distance and computes the average predictions for the retained data points. Distance measure and threshold both affect the output of IPDP. Because we accept data points below the distance threshold, if the threshold is too low, then very few examples will be accepted and the PDP will not be smooth. Note that since distances are normalized to a value between 0 and 1, setting the threshold to 1 converts IPDP to PDP. We tested IPDP on the cervical cancer dataset using a gradient boosting classifier to evaluate the difference between PDP and IPDP. We will now discuss how threshold setting affects the results of IPDP. These figures illustrate the difference between PDP and IPDP when the threshold is set to 0.8 and 0.5 for the age feature in the dataset. Figure 1a shows that PDP is unable to capture any interesting observations for the age feature. However, we see in Figure 1b that the data does exhibit some patterns. Specifically, for some examples, shown at the bottom of the figure, a change in age has no impact, whereas for others, as shown at the top of the figure, there is a slight uptick in the probability of cancer prediction as age progresses. The bottom two figures show the IPDP for the age feature. Figure 1c shows that a high threshold does not capture any interesting information as more data points will be accepted, as seen in PDP, whereas in Figure 1d we see a slight uptick in cancer prediction probability at age 50. In Figure 2, we see the difference between PDP and IPDP when the threshold is set to 0.5 and 0.25 for the years spent smoking feature. Figure 2a shows that the PDP is unable to capture any interesting observations for this feature. However, we see in Figure 2b that the data does exhibit some patterns. Specifically, for some examples, shown at the bottom of the figure, changing the year spent smoking has no impact, whereas for others, shown at the top of the figure, the probability of cancer prediction is higher. The bottom two figures show the IPDP for the year spent smoking feature. Figure 2c shows that with a threshold of 0.5, IPDP captures some variation in the probability of predicting cancer, whereas in Figure 2d with a threshold of 0.25, we see that the figure begins to display the effects of a small number of examples being averaged, resulting in spikes in the probability of predicting cancer. We will now discuss the results of PDP versus IPDP. In PDP, results can show overly smoothed interpretations for local features, whereas IPDP captures finer feature interactions, and we know now that threshold tuning impacts IPDP sensitivity. We will now discuss how distance metrics affect IPDP. The L1 distance measure, as outlined in Equation 2, is used in Figure 3. In Figure 3a, we see the PDP results for the number of packets of cigarettes smoked in 1 year, where the PDP result was uninteresting. In Figure 3b, we see a more interesting result with a threshold of 0.6, with a minor increase in the probability of cancer as the number of packets smoked per year increases. In Figure 3c and d, the variation and increase in probability is more pronounced, with the low values in Figure 3d beyond 5 likely due to a lack of data. Again, in Figure 3d, we see that a small threshold results in a non-smooth function. For a threshold value of 0.4, L1 and L2 perform similarly, as seen in Figures 3c and 4c respectively, while the cosine distance measure begins to show an increase in cancer prediction probability as the number of packets per year increases, in Figure 4d. Finally, for a threshold value of 0.2, both L1 and L2 perform similarly, with L2 showing slightly less sensitivity as seen in Figures 3d and 4e respectively, while the cosine distance measure shows an increase in cancer prediction probability as the number of packets per year increases. Of the three distance measures implemented in this study, cosine distance was the least sensitive in IPDP. However, cosine distance is usually used in text analysis problems and thus may not be suitable for the cervical cancer dataset. The L1 and L2 distance measures perform similarly, with L2 providing smoother functions overall. We will now discuss the key findings of this paper. Firstly, IPDP mitigates the limitations of PDP. Secondly, the choice of distance metric and threshold is crucial in the efficacy of IPDP. Finally, IPDP improves the interpretability in complex models. The advantages of IPDP include more reliable feature effect estimations, handling correlated features effectively, and providing customizable interpretability options, whereas the limitations of IPDP include computational cost due to distance calculations, choice of distance metrics impacting results, and needing domain knowledge for tuning the threshold. Future work includes exploring alternative distance metrics, applying IPDP to other datasets and models, and integrating IPDP with other interpretability tools. In conclusion, IPDP enhances PDP for better interpretability, reduces misleading feature effect estimations, and is very useful in transparency in machine learning decision making. Thank you very much.